Hey everybody, in this video we're going to be talking about a basic LRFD beam loading problem. We're not going to be talking about beam design in this problem, but we are going to talk about the weight of this beam and how that affects the entirety of the problem. So here you have a simply supported beam that we're looking at sitting on two rollers, so we don't really have any forces acting on this other than those acting in this direction. Now when we're talking about beam analysis, you may say in terms of loading, the main thing that we want to figure out is how much load is actually being applied to the beam at first, and you're actually correct on this. But as you may remember with LRFD, we have some load cases and load factors to deal with. Now, previously when you may have looked at LRFD loading, you say, well, there's 5 equations, I'm going to have to go through all of them and it takes me a ton of time. But actually, if you look at the equations and understand them a little bit, you're going to understand that in most cases where you only have a live load and a dead load, you're always going to be controlled by equation 2, which says 1.2 dead plus 1.6 live is going to give you your load case. And you'll figure that out after trying it a few times if you haven't already, but this is basically how it goes. If you look at the equations, you're going to see this is what's going to end up mattering at the end of the problem. So if you remember this in these types of problems, you're good. Now, you may be a little bit confused too, because when you're looking at this, we're seeing 2 different types of loading. I should have also mentioned this is a 35-foot long beam. But when you have this situation here, we're going to have to calculate these loads separately and factor them separately. Then we'll add them together and we can use that to figure out how much is going to be applied to the beam. So I'll start doing this with the point loads first, because that actually makes sense and it'll help you out later in the problem when you have to get through the steps where you would actually be doing beam design if you calculate these out separately. So our point loads are both live and we have 2 of them. One is 20 kips and one is 10 kips applied at points A and B over here. We don't really care about where they're located on the beam right now. What we really care about is how much they are, because we're in this step. So we're not going to have a dead load in this case, so it's going to be 1.2 times 0 plus 1.6 times 30, because we can just sum them. You're going to add those together. 1.6 times 30 is 48 kips. So now you have the factored point loads. If we take this equation again, 1.2 dead plus 1.6 live, we are going to see that we have a different situation now, because we're looking for W, which is this distributed uniform load that we're talking about here, and we have a live load and we have a dead load. So if we do this, we're going to have 1.2 times 400 PLF is our dead load, plus 1.6 times 500 is our live load. That's going to give us 1.2 times 400 plus 1.6 times 500 is 1,280. Now remember, this is not the same unit. This is in kips per foot right now. Pardon me, pounds per foot. And this was not pounds, or this was kips here, yes. So the other way you can look at this is 1.28 kips per foot. But we have 35 feet, right? So we're not done here yet. If we're looking at the total loading that is acting on the beam, also, this is wrong. This is actually a shear load. When we're looking at this right here, we have 1.28 kips per feet. We need to multiply that by the length, though, to figure out what the total weight is going to be. 1.28 kips per foot times 35 feet is going to be 44.8 kips. So if we sum those together now, we have 44.8 kips plus 48 kips. We now have 92.8 kips. All right, so that tells us how much shear load is going into the beam. That's one way you can look at it. But if we got into a design problem, which we're not really focusing on right now, keeping these separate would be helpful, because it helps you determine the different types of loading that you're actually concerned about and whether your beam is going to be adequate. Now, you may think that we're completely done in this case, but there's actually one more step that we need to think about here. as you noticed, this up here is the self-weight of the beam. Now, depending on the problem, or this is the section size of the beam. Depending on the problem, you may or may not have to include that in the problem, or depending on the stage, you may or may not have to include that in the problem. So this was our loading here, but let's see what happens if we include the self-weight of the beam. All right, so now we're going to have an additional dead load here. So this was 400 pounds per foot. This is now going to be 435, because an 18 by 35 is going to be 35 pounds per foot of dead load, plus 1.6 times 500. Still, that live load has not changed. 1.2 times 435 plus 1.6 times 500 gives you 1322, or 1.322 kips per foot, also known as KLF, which is kips per lineal foot. And you can see that these numbers here are really not that much different, which is why in the early stages of these problems you can often neglect the weight of the beam and then come back to it later, throw it into your equations to make sure that it passes, and then you will most of the time be fine. So for this problem, we went through, we looked at the LRFD load combination that was going to govern the case, which is 1.2 dead plus 1.6 live, because we were given a live load and a dead load. If we had been given different types of loading, we could have ended up with a different situation, but we weren't given that, so this is what we were working with. We were given 2 live point loads that we went through and factored to get a point load of 48 kips, and then we were able to take the distributed loads, both dead and live, and figure out what the weights would be, including and not including the self-weight of the beam. And then we actually didn't do this for the final weight here, but you understand the idea. We were able to calculate the final total loading on the beam by using 1.28 kips per foot, which we were given from WU up here, multiplied by the 35 feet, and then we were able to get 44.8 kips, which when added to the 48 kips from the point loads gives us a total load on the beam of 92.8 kips. This number here is really important if you were to come back and you were going to work on doing end reactions, if you were going to do your shear and moment diagrams. We'd need some additional information to be able to do that, but we're not going to handle that right now. So I hope you guys found this video helpful. If you did, please feel free to like it, leave a comment, and subscribe. It would really help the channel out, and it helps bring this content to more people. So thank you guys for watching. I hope it was helpful.